All right, so we're back onto another chapter, Chapter 8, Linear Regression. This is where we're going to use correlation to create a line that models the association. Like every model, it's not going to be exact, but we're going to see how good we can get. Okay, what we want to see is if we standardize our variables, we'll talk about that again in just a second here, the best fit is a slope equal to r. We're going to see how that happens. We're going to find the equation line using summary statistics and correlation, using the calculator, and finally by reading output from computer-generated software. Okay. Lastly, we're going to interpret slope, the y-intercept, and the value of r squared in context of the problem. So let's go ahead and start. First of all, the regression line. It's also known as the linear model. Sometimes it's called the line of best fit, and this last one, which you also have to know, the line of least squares. It's a straight line. It supports a prediction of a response variable, or the dependent response variable, y, for some given value of the independent or explanatory variable, x, by measuring the error. Now, we're going to use dependent in this, but be careful. We're not assuming causation. Just one of them is the independent, one of them is the dependent variable, because the value of our response variable is going to depend upon our model and the explanatory variable, the value of that we put in. Now, residual. It's just a difference between the observation of y and our predicted y, hence its error. It's how much were we off from reality. Now, we're always going to find the same way. Residual is the actual value minus the predicted. Predicted is going to be a y hat. We're going to see where the y hat comes in again. It's just how far away were we from our line of best fit. So negative residual, we overestimated because our prediction was greater than actual. We overestimated. A positive residual, we underestimated. We had more left over. Line of best fit is designed to minimize, and this is kind of odd, so I'm going to talk our way through it. It's designed to minimize the sum of the squared residuals. In our picture, I have here a small scatter plot. I have a line of best fit going through it. My error is how far each one of those points is away from the line of best fit. And I square it in order to make all those values positive. Some of those values are negative, some are positive. The sum of the residuals is going to be 0, but the sum of the squared residuals tells me how wrong was our data overall. So some important facts to remember when you go to make this linear model. First of all, has to be quantitative variables. Okay? The data also has to be straight enough, and that we get that from looking at the scatter plot, and does it look reasonably straight. Lastly, outlier. No point has to be singled out for special attention. So if you have outliers that are causing a significant influence, we want to mention that, and we might have to calculate it with and without the outlier. Now remember, correlation doesn't care about the difference between the explanatory and response variable. That if I put my explanatory on the y-axis and my response on the x-axis, my r is still going to be the exact same. I might try that today just so we can see how that works. Now remember that as correlation goes less strong, the prediction moves less in response to changes in x. Our error is also likely to get bigger. So the weaker our correlation, the closer it is to 0, the less I'm going to see changes. Regression. You have to know the explanatory versus response because regression measures distances in y direction. Okay? Changing the variables is going to change the line's vertical and horizontal differences. So if you change the variables, you're going to change the line. Now the point, x bar, y bar, is always going to be on the line. X is the mean of all the x values. Y is the mean of all the y values. So if I measured height and hand span, the mean of all my heights and the mean of all my hand spans, that point will be on the line of best fit. My line of best fit has the form y hat, and that's that y with the small caret on top means, it says y hat, equals a plus bx. A is my y-intercept. B is my slope. Now, I know in algebra we're used to seeing y equals mx plus b as one of the slope-intercept forms for a graph. In statistics, we use y hat equals a plus bx. We're talking about predictions of y. Also because how their calculator gives it, and there's lots of reasons to use this, but this is the way we're going to use it. Slope, b, it's equal to r, my coefficient of correlation, times the standard deviation of y divided by the standard deviation of x. So it's still got a slope in there. It's rise over run. Standard deviation of y over standard deviation of x. Since standard deviation is always positive, the only way you can possibly get a negative slope is based on r. R controls which direction my slope is headed in, positive or negative. Now, slope is the estimated unit rate of change of response per unit rate of change of the explanatory. It means just what it says, but let's put this in English a little bit more. If I was graphing this, slope is telling me how much does y change for every change in x. So let's say I was going from here, I was following a slope of 1. Then for one change in x, I expect one change in y, I'd have a slope. So for every single unit change in x, out of a single unit increase in y, well, that's a slope of 1. If for every change of 1 increase in x, so x goes up by another 1, but y decreases by 2, well, then I have a slope of negative 2. We're talking about unit change. Every time x changes by 1, how much does y change by? That's all slope is telling us. Y-intercept. Now because y bar and x bar are both in our equation, we said our equation equals y hat equals a plus bx. Now we said y bar is going to be on our line. Well, I can rewrite this then as y bar equals a plus b times x, but this time it's actually going to be x bar. So I can rewrite this as a equals y bar minus bx bar. So I can find my y-intercept. If I have my slope, I have the means, I can find my y-intercept. Now, some things that we do with this information, we can do interpolating. Interpolating is when the equation is used to predict a y value for an x value that falls within my x data set. So let's say I take people's heights. The shortest height I had was 63 inches. The tallest height I had was 74 inches. And they want me to make a prediction for someone who's 65.5 inches tall. Well, I'd be interpolating. That data falls within my data set. I can also do extrapolating. Now, extrapolating is when I use to make a prediction. I use my equation to make a prediction for a y value using an x value that's outside my data set. So again, if I had everyone's height from 63 to 74 inches, that was my sample, that was my data set. And they come in and say, okay, well, what would it be for someone who was 60 inches tall? That's outside my existing data. My guess isn't going to be backed up as strongly as if I was interpolating. I don't have data to support that necessarily, but I can still make a guess as long as it's not too far from my data. But it's probably, I'm not going to have as much confidence in that answer. It's outside of my data set. Now, we've got some things right here. I said B is the slope of the line at best fit, and that's true. R is the slope of the line if we standardize our data. If I turned all my x's into z-scores and all my y's into z-scores, then I'd have standardized my data. What I mean was I would take my individual x's minus the mean of all the x's and divide by the standard deviation of the x's. Now, if I did that for every x, I'd have z-scores for every x. Similarly, I take all my observed y's minus the mean of all the y's, divide by their standard deviation of y. I've turned all my y data values into z-scores. I'd have standardized it, which now means r becomes my slope because my standard deviations just turned to 1. And we said slope is equal to r times the standard deviation of y over the standard deviation of x. And when I convert these to z-score, these both turn to 1. So I'm doing r times 1. Slope is now just r, which means for every time x would increase by, every time x changes, r moves that number of times standard deviations of y. So let's go through and try a couple of these. Let's say I have a scatter plot of houses in prices in thousands, or thousands? Yeah, thousands of dollars versus house size. Now, I say the relationship is straight. There's some moderate scatter, no outliers. And the correlation between house price and house size is 0.85. So if a house is one standard deviation above the mean in size, making it about 2,100 square foot, how many standard deviations above the mean would I predict its sale price to be? Didn't realize that was on the screen. Well, remember, it doesn't care which order I do these in. R is R is R. R doesn't change. It doesn't care. So a 1 standard deviation change in house size is going to be a 0.85 standard deviation in price because our slope is 0.85. For every standard deviation change in 1, the other change by 0.85. Remember, R didn't care which order I did these in. Okay, R would be the same if I flip these. Now, personally, I think house size is more likely to explain the difference in house price. But recall, R doesn't care. If I was trying to say the price explained the difference in house size, my R would still be the exact same. So for every unit change, 1 standard deviation is a unit. For the mean and size, then the price would change by 0.85 because R doesn't care which order they're in. Let's try another one. So what would you predict about the sale price of a home that's 2 standards below average in size? So I've got my house size, my sale price, and R was 0.85. Well, if I'm 2 standard deviations below the mean for house size, I'm somewhere over here, I'm going to be 2 times 0.85 for sale price, or negative 1.7. So I'll be 1.7 standard deviations below the mean sale price. And that's exactly what we found. So R squared. So we're kind of going kind of quick on this. Some of these concepts we have to play around a little bit, but we go kind of quick through most of this one. So we had R squared and regression. In R squared, the coefficient of determination, that's R squared, gives us information about the percent of variation of the values y that can be explained by the least squares regression line. There's a certain sentence we remember. Variation, our R squared is a percentage. So we're going to say this percent of the variability of, and this is our y, is accounted for by our model, and actually our linear model of x. So this is what R squared gives us. R squared is a measure of the percentage of the variability that has been accounted for. So we're going to try this. So let's say my R squared between the independent variable height and dependent variable weight was 0.83. Okay, that's my R squared. Now I can include 83% of the variation in weight can be accounted for by height according to this model. Now, that's not exactly the same sentence as I have here. It doesn't need to be. But it does have to have those 3 points in it. It has to talk about the variability is being accounted for, and it has to tell me about it's a model. And in this case, we're using linear models still. Now, alternatively, I can also say 17% of the change in weight has to be attributed to chance. Maybe I did some errors in measurement. Maybe there's some sampling bias, interviewer error, all types of things. Chance or error, or to some other variable not included in the model, in our linear relationship we've developed here. Now, some important things to note. First, the sum of deviations from the mean, not the square deviations, just the deviations, is 0. If I don't square them, some are negative, some are positive, the deviations from the mean is going to be 0. Sum of the residuals is going to be 0. Mathematically, the way they're found, we're going to get 0 if we summed all the residuals, which is why we have to sum the square of the residuals, because some are positive, some are negative. We square them, they all become positive. Next one, remember, R squared is always going to be greater than, it's always going to be greater than or equal to 0. It's going to be positive. But that doesn't mean R is greater than 0. Remember, we squared R to get R squared. So if x and y are negatively associated, then R is going to be less than 0. For example, I have 2 scatter plots. These 2 scatter plots have, I believe I made these, they have the same R squared. But clearly, one is a positive association, one is a negative association. So if I gave you R squared and asked for R, well, if both of these have an R squared, 0.25, I'd take the square root of that and find it's 0.5. But This one's R is positive 0.5. And this one's R would be negative 0.5. We'd have to look at our scatter plot to see that. Or we'd have to see something tell us there was a negative association, and then we know the sign to put on R. Least square regression models are only good for making predictions when the data plot looks kind of linear. If it's curved, I can't use it. Okay? But how can I tell if I'm using a good model without using my eyes? I look at the residuals. I can look at the residuals. Residuals should display a scatter plot of points, and that's just my x, and then my residuals, graphed the residuals against their x values. Okay? So my difference between the observation and the prediction with the x value still being used for the plot. Now the average of the residuals is always going to be 0. But if there's a definite pattern in the residual plot, then a linear model is not good for the data. And we can go into some pictures here of why. So let's say I have a curve in my residuals. So they start off below, they cross my 0 line, come back under. Well, the linear model wasn't a good match, because let's see what must have happened. So let's say this is my scatter plot, and let's just say this is my line of best fit. My residuals tell me, well, my first few points are below the line, and they're getting closer to it, and then they cross the line, because now I have positive residuals, and then they cross the line again, I get negative residuals. My data is clearly curved. Anything you can do, I can have unbalanced. I have a lot of points up here, and just a couple down here. Well, then I had a line of best fit. I had a lot of points with a positive residual, and then a couple down here. There's something odd going on with this. This is a particular kind of case where these points may have been unnecessarily affecting the outcome. Okay? Could show me, it could potentially lead to outliers. Okay? Could be. The other point is there's just too many above the line. This line is supposed to be looking a line of best fit. And if most of the points are above it and only a few below it, that's not a line of good fit. It's not really modeling my data. Last thing I'd have is like a megaphone, or I call it fanning. So what I see is that data is getting further away from the line as it starts. That means I have my line of best fit, and my data was very close to the line at first, and then it started going away from it, and then it's doing the same thing in the other direction. It's fanning away from the line. Really what this suggests to me is maybe I have two population groups that are distinct. And the first one has curved data that way, and the second one has curved data this way. But either way, the linear model was not the best one. And sometimes you'll simply see it in one direction, that megaphoning, the fanning. What you're seeing is you see some points are staying close to the line, and then it starts getting further and further. You see a trend doing that. What we want to see is just a random plot for our residuals. If it's random, that means there's no information left as far as where the points were relative to the line. But a clear pattern of residuals indicates variances are not staying the same. What I mean by that is we look back at our lines again. If we look at this first line, the variance, how far it's from the line, it's not staying relatively the same. It's getting smaller. Now it's getting larger again. Now it's getting smaller and then larger again. Okay? Make another one. If I have a line of best fit like this, my variances like this, they're not all identical, but I'm seeing a randomness to it. But if I'm doing this, more points further and further from the line, my variances are changing. In fact, they're increasing. I'm going to see a fanning behavior on the residuals. Now we're actually going to try this. So if you've got the calculator already, if you've got your TID4, you want to use this, load this down in your TID4. What this data represents the number of books on someone's desk and the depth of paper on that same student's desk, chosen at a random time. So first thing I'd ask myself is, which one do I think will predict the other? Which one might explain the changes in the other? So take a moment and think about that. If you need to, pause the video. Now, personally, I think about the more books someone has for classes, the more notes they're going to have to take, possibly more homework. It seems reasonable the more books someone has, that's going to affect how much paper is on their desk. It may increase it. On the other hand, it could be the more books they have, the less notes they have to take in class, so maybe they'll have less paper on their desk. But either way, the books, to me, suggest which way the paper is going to go. So that means I get to load my books in L1. I'm going to load the inches of paper in L2, because I need to look at a scatter plot of this data. So pause the video You load this data in L1, L2. Alternatively, if you haven't got the TI-84, if you haven't got Rabbit Emu as an emulator, if you haven't got any kind of emulator in front at all, you should have that website I've shared before, or I'm sharing on the Google Classroom, that you can load these and create a correlation. Of course, that website only gives you some of the information the calculator would give you. So I highly recommend using the calculator for this. So pause video, load that data in the calculator. Okay, now if you're back, that tells me you've loaded the data. So I have something like this, L1 and L2. I want to look at the scatter plot. So I get out of my lists here. My second, y equal. Stat plot 1 is turned on. That's what I want. And it's set for L1, L2. So I quit out of this screen. And I just tell it zoom. And tell it zoom 9, because that's my stat plot. And there's my scatter plot. Okay, so it looks pretty straightforward. It looks kind of linear. I don't see anything majorly odd in there. I don't see any clear curves, at least. Also, it appears to be, I'd call this one positive. It looks like it's going positively. Moderate strength, maybe. Not sure yet. I'll have to look at R to actually know for sure. Like I said, linear. And I don't see any outliers. This one's going to be a little concerned, but we'll take a look. Okay. Next thing we want to do, I want to run the linear regression. And this time we want to save the line in Y1. Let me show you what I mean by that. So we've got our calculator. We've ran linear regression before, so we exit out of there. We know it's in, whoop, let's get out of there. Stat, calculate. We said linreg, and we said we're not using 4. We want a plus bx. There's my a plus bx. So stat calc 8. It's set for L1, L2. For instance, blank, it says store linreg. Store the regression equation. Store linreg. Store reg EQ. So we want to store it. We want to store it in Y1. Y1 is a variable. So I go to vars. It's a Y variable. So I go to yvars. And it's a function. I'm going to save a line. I'm going to save it in Y1. I hit enter and enter. And here I've got my R value, 0.62. So it's moderately strong. It's definitely not weak. It's positive. 0.62, it's positive, not moderately strong. It's not very strong, but it's moderately strong. Okay? And it's going to now, here's what happened. When we did that, our calculator calculated all the residuals and saved it in a special list called resid. Now previously, we've seen lists of L1 and L2. It has a special list inside the calculator where it has just saved an information called resid. Now we want to plot those residuals against X. We want to plot the residuals against L1, or the number of books. So let's go ahead and bring that up. So we get our calculator. This time we go back into our y equals. And we have L1. We want to keep that L1. I want to change this to residuals. And it says a special list. So you look here, the words in blue, right above stat, say list. So second, stat. And here's our resid list down here at 7. That's all 7. Now I hit enter one time to save that information. Now, because I've changed what I'm graphing, I have to tell the calculator I've changed what I'm graphing. So I don't want to zoom into where it was looking before. I want to look at this information. So I have to tell it zoom 9. And here's my plot of my residuals. And there's actually a few things on this plot. First thing is the points, these are my residuals. This dark line running through the middle, this is 0. Now I can see the size of my residuals by hitting trace. So when x was 1, y is negative 0.829. When x is 3, y is negative 2.93 or 2.94. I can progress through these. When x was 5, y was negative 1.5. I can get all of my points and figure out what my axes need to look like. Now if you notice though, there's one other point or one other thing on this graph. And that's this line running through here. This is not part of my residuals. It is not part of my residual plot. Instead, it's this line. This is our y hat. Y hat equals this equation. It's a very long one. That is not actually part of our residuals plot. We don't need this line. If you have plot residuals, you do not include this line. And in fact, Residuals are the distance from the line of best fit. Well, that means this point must be on the line of best fit. This point must be a little below the line of best fit. This point must be a fair bit above the line of best fit. When you're looking at residuals, the 0 line, that would be the line of best fit in the original model. These points are fluctuating around the line of best fit in the real one. And that's what 0 line is on the linear model, on the residuals plot. There's kind of something interesting to think about, and we'll see when we look at the scatter plot again. Okay. Like I said, this is what it would look like. There's no pattern in it, so the linear model was a good fit. That's all we need to see. We saw residuals. There's no pattern in the residuals. Linear model was a good fit. Now, let's go back into that. I want us to actually see the scatter plot with the line of best fit. So let's go back in a second. Stat plot. Go into it. And rather than applying the residuals, let's go ahead and plot that L2. And now we'll look at it again. Zoom, 9. Just like we saw before, some of our points are above the line, some of the points are below it, and we have the one that's right there on the line of best fit. So we can kind of see what our residual is going to look like. Our first point was going to be below 0. Next point is going to be above. Then we have one below and one above. Then one below, one on, one above. We're progressing as we go through X, then one above, and then one below. And if we look, that is what we saw. That is what we saw. Below, above, below and above, below, below on above, and then below. But nice, clear, there's no pattern. Some points are close to the line on this side, some are close on this side, some are far apart on this side, some are far apart on this side. That's what we want. Nice random residuals. That tells me my linear model is a good fit. So let's try this data. I'll construct a scatter plot and describe its shape. So take a moment, load this data in your calculator or on the website where you can view these, then come back to the video. Okay, so at this point, so scatter plot looks something like this. What does that shape look like to you? Remember, to describe it, you have to tell me 4 things. You have to tell me direction, form, strength, and whether or not there's outliers. Now I look at this, it looks like those points are all pretty close to the same line, so that tells me it's strong. It's pretty clear it's positive. As x increases, y is increasing, so that's a positive slope. And it looks pretty linear, so that's what I'd say. I have a strong, positive, linear association between height and weight. I've told it in context. Now, I want to find the least squares regression line. It's another name for the line of best fit, the line of least squares, the linear model. All those names mean the same thing. I want to find the correlation coefficient and the coefficient of determination. I said, pause the video. Let's try and do that. All right, so if you're back, all that data should have been loaded in a calculator. And here's where I have mine. I put mine in L3 and L4 this time. So I have my height, and I have my weight. Now to find all these things, I want to run that same regression we ran before. So I hit Stat, Calculate, 8. Where's my x's? Well, I put them in L3, so I tell it L3. My y's are in L4, so I tell it L4. Parentheses are blank. Store the regression equation. Yeah, I want to store that. Let's store it in Y1. So I can overwrite the one I've used. That's fine. I tell calculate. And I've got my regression line. I've got my R. And I've got my R squared. So my line of least squares is, it tells my calculator y equals a plus bx. So y hat equals a, negative 52.49 or negative 52.5, plus b, 3.04 times x. My coefficient of correlation is r, 0.9681. My coefficient of determination, 0.9373. Right here on this screen. So I wrote my equation. Y hat equals negative 52.5 plus 3.04 times x. R, 0.968. R squared, 0.937. I want to interpret the slope and coefficient of determination. Take a moment, refer back to what we said about slope. We said something about for every unit change in x, there's a slope change in y. So we were talking about height and weight. So for every 1 inch taller someone is, I expect their weight to increase by 3.04 pounds. Now I want to talk about coefficient of determination. So determination is that r squared. We convert to a percentage. So it'll be 0.937. That's going to be 93.7%. We said it talked about our height to weight, and it's talking about our model. Take a look back in notes. Pause the video for a moment. Try to figure out what you think it is. All right, so you're back. So we'd say that would be 93.7% of the variability of weight is accounted for in our model of height. Where did I put here? I put it a little bit differently. 93.7% variation in weight can be explained by height according to this model. That's it. Kind of the same meaning either way. Now, I like this one. I think I like this way a little bit better than what I said it as first, though. Right. Calculate residuals and construct the residual plot. Well, we haven't done this one by hand. We said the calculator's been doing it for us, and we could just get it in the list. But we can actually calculate them also. Let's pull up our calculator. Let's take a look at this. So I go to Stat, my little mouse, and we go to Edit. I put my height and weight in L3, L4. Well, L5, I don't need that in there. Let's clear out L5. I can use L5. I have my equation of the line. We said line of best fit is y hat equals negative 52.5 plus 3.04 times x. Okay, so my residuals are, well, they're going to be the actual data minus the prediction. So my actual here is L4. So I'd say, well, let's see something here. Go up to L5 and I hit enter. I want to calculate all these data for me, all these points for me all at once. So my actual, well, that's inside of L4. So we're going to tell it L4 minus the prediction. We'll put parentheses. And my prediction was the y-intercept, negative 52.5, negative 52.5 plus b times x, 3.04, 3.04 times x. And in this case, x is saved in L3, so I'll tell it L3. And close my parentheses. So there's my residuals. My first one's negative, so my first error is going to be below the line. Second one's 5.05, negative 0.54, 6.3, negative 11.9. Those are my residuals. Just like that. I think I used a bit more of the data when I calculated this first time. So I can construct the residual plot. And we said there's a couple ways to do it. One, I have the residual manually loaded. So I go in here to plot the residuals. I go second y equals. I go in. Now right now it's set to do L1 and the residuals, but I'm not using L1 anymore. Our x's were now saved in L3. And the residuals, which were saved once I reran it. So now I can zoom in. Oh, I've been waiting for this to happen. This is my error screen. Happens sometimes. You're on this screen, you'll sometimes get this error. All you have to do, hit second quit. So try again. Zoom. We're going to zoom to our stat. There's my residuals. As we said, my first one should be a little bit negative. So it's a little bit negative. Second one, positive. Quite a bit more positive. First one was negative 0.35. Second one was 5. Then negative 0.46. Then positive 6. Negative 11. Negative 6.9. Positive 7. So I don't really see a clear pattern. Some of them are above the line, some of them are below, some are close, some are far. We're not really seeing a clear pattern there. But that's what we got. Now the other thing is, We'll explore 74, 180 as a possible outlier. So let's go back over to our calculator again. We were wondering about 74, 180. Could that be an outlier? So let's look. Here we are. We hit trace, and we want to find where is that value. So hit trace. I mean, for my x is 74. So there's my x is 74. So the point doesn't seem ridiculously far compared to some of the other ones. So it's not that far from the line of best fit. Okay. I can also look at it on the original scatter plot. Changes back to L2, or I'm sorry, L4. And again, we have to tell it where to zoom in. And there's my line. I hit trace to find that 74. 74 is actually, it doesn't look like it's that far from the line compared to the others, so I don't think I'd call that one an outlier. And same way we did it, we found it each way. It doesn't look like 74 is that far from the line. It doesn't look like it's really an outlier. In fact, if it wasn't there, my line of best fit might be the exact same still. It doesn't look like it's having that much of an effect on it. Right. So let's see what else we can do. Now, let's talk about the goodness of fit of this model. Let's go back and look at those. We got our residuals. We got our scatter plot. We had our R and our R squared. That we used all those values. Let's go back and look at those again. R, 0.96. R squared, 0.937. So scatter plot and residuals again. Residuals, kind of random. Scatter plot looks fairly linear. Well, doesn't appear to be any obvious curve to the data. Not in the residuals and not in the original scatter plot. R squared's pretty high. Seems this is a reasonable fit. No clear curve, no clear patterns in my residuals. R squared is nice and high. This looks like a good fitting, well fit. That looks like a fit that's going to be pretty good. Now, this looks like a pretty good model, so how much would I predict someone is going to be? How much would I predict a person who is 57 inches, how much would I predict they weigh? Well, I'm going to use my model. Put 57 inches in for X. So I'm going to call it my prediction. I'm doing that in calculator. Let's pull it up. Set your calculator. We have negative 52.5 plus 3.04 So I put in negative 52.5 plus 3.04 times 57 inches for their height. I gotta click it. There we go. So our prediction is they would weigh 120.78 pounds. That's our predicted value. That's exactly what I found before. Oh, lost it. Let's get back on screen. There we go. We plug around the formula, multiply it, 120.7 pounds. That's our prediction based on our linear model. And that's it. That's how we use these. Last thing, what does the regression line tell us about heights and weights in this sample? Well, the regression line tells us there's a positive relationship between weight and height. That's it. Same thing that R told us. Remember, R is controlling the slope of our regression line. Person's height increases, their weight tends to increase. It kind of makes sense. And that's it. So, from here, log on the web work, knock out the questions for Chapter 8. Look forward to seeing everyone in class soon.